Hello, everybody. I see that folks are starting to come in right now, so I'm just going to get started with the introductions. Thank you, folks, for coming today to the Michigan Energy Summit Afterglow Series. We had so much content at the Michigan Energy Summit, and thank you so much for your responses and your feedback on that. We can't wait to be in person again, but we're really glad to be able to continue the information for after the Summit Series itself. So welcome to the Afterglow Series. The first of many is how consumers' energy can help you achieve net zero. It's not that scary. It's not something like a pie in the sky. It's very achievable, and these folks are going to tell you how to do it. A few housekeepings before we begin. I mean, I know everyone's zoomed out, but just to make sure we got it clear, the chat is where we're going to send links to you, where you can comment to each other. And the Q&A is specifically questions that you have for the speakers. We'll be having a really robust Q&A session at the end of the call, so don't forget to put your questions in immediately when you have them, because you know how it goes. 5 minutes later, you already have another question, right? Lastly, there's going to be a survey and an email following up on this webinar. We're going to have a recording of this one too, in case you're going to miss anything. And make sure to fill out that survey because your information is very valuable to us. We actually do take your feedback and put it into more webinars. And lastly, thank you to our sponsors, Consumers Energy being one of them. So thank you, Annie Cook, for speaking with us today. If you can go to the next slide, I'll be able to introduce you folks. We have the pleasure of having Annie Cook. She's a mechanical engineer for Consumers Energy. Umay Akkoseoglu is the energy engineer for the DNV-GL. And lastly, we have Sean Armstrong. He's the Zero Energy designer and managing principal for Redwood Energy. But you come here to speak to me, and you came here to talk to Annie. So Annie, please take it away. I'm really excited to hear from you.
Thank you, Jillian. All right, so today we're going to talk about Consumers Energy's Zero Net Energy Pilot Program. It's been up and running for about 3 years now, and I'm the pilot program manager. And the reason that we have this program is because of all the traction that is happening these days with reducing energy consumption, but also carbon reduction goals. And as you all know, Governor announced the carbon neutral by 2050 goal. And so our program ties into that very nicely in the fact that we are looking at energy reduction, carbon reduction, all electric, whole building approaches to your design. Consumers Energy has their clean energy plan as well, which ties nicely in with the carbon reduction goals for the state. And we're just looking at going coal-free, net zero emissions, more renewable energy, smarter energy, and more customer control and flexible strategies. This is the path forward that Consumers Energy is looking at in transitioning with their electric capacity by fuel source and switching over to a more renewable efforts and also looking at investing higher in the customer efficiency program. So starting out right now, we're looking at about 10%, and we need to double that, more than double that by 2040 to reach our goals. And that's where this type of a program really comes into play. So, Zero Net Energy. I know it can be a little daunting, and also with our all electric requirement for the program, that is something that people typically balk at right away because not having experience with it. And that's fine. This is a new frontier for a lot of people, and we are here to help you in that process. So this program, as I said before, has been up and running for about 3 years now. And we've had a lot of lessons learned in that process and really trying to help the market move forward in this capacity. The program is open to commercial customers as well as multifamily and mixed use, obviously, in there as well. We are a ZNE ready requirement. As this is an energy efficiency program, the incentivization goes towards the energy reduction. So although true ZNE is going to include renewables, whether that's offsite or RECs or whatever fits your budget and site, for our program, that's up to the customer to decide what they want to do on the renewable side. And whether that is down the road doing renewables and setting up to be solar ready, which is a requirement of the program if you can't do solar at this time. That is still just kind of an open spot. We are focusing today, and for the sake of this program, on the reduction side. And the requirements as far as that is concerned, ideally we'd like to have 25 kBTU per square foot per year. That's an EUI, so that's taking your energy consumption of the building and dividing it by the square footage. But we also recognize that that's not achievable for all building types. We have different uses in our program. We have existing buildings that are going through major retrofits and have limitations, and we also have new construction. So another requirement that we've put into play is 30% reduction, energy reduction, not energy cost, but energy itself reduction for major renovations, or 40% for new construction. And the incentive that you get for this is $1.50 per square foot. And some of the other benefits that you get from this program is the technical assistance. We're there for you from start to finish, going through, and we're trying to really give you that education to enable you to run with this. Like maybe you have your first project in our program, but this is meant to be scalable. These are skills and processes that you can apply to any project that you're working on. And we're trying to show this through having Michigan case studies to show you that yes, ZNE all electric is in fact feasible in the state of Michigan. It's not just for California anymore. And we have our zero net energy design guidelines. And that is something that we are talking about today. And this is something that is showing very specifically in Michigan how you go from a code minimum project and what it takes to get to a ZNE project, and what the technologies are, what kind of effort you're going to have to put in. And oftentimes, surprisingly, it's not breaking the bank. It's not the most expensive things out there. It's really just mindful design at an early stage. And we're showing you how you can do that without adding a whole bunch of costs onto your project. We are also doing a lot of educational sessions like today, and we'll be doing more in the future. And we have our Zero Net Energy deliverable guidebook. And this guidebook takes you through step by step, showing all the deliverables that are required for the program and how to do them, and gives you resources and templates, all the things that you need to make this as streamlined and easy as possible. And that goes into the ZNE roadmap as well. Some of the things that we like to encourage here is early design involvement. That's extremely important in order to minimize rework. If you're deciding at like 50% CDs that you want to go ZNE, it's going to be really hard. And you might have to go back and redo some of your design. And that, I mean, if you look at cost for equipment, that's one thing. But if you're looking at cost for labor to go back and redo and lost time in order to get your project finished, that's extremely expensive. So having these conversations from the start with all the involved parties that are going to have a stakeholder investment in how the building gets operated, that's the best way to go about this. We also encourage cost benefit analysis to make sure you're picking the equipment that is relevant to your project, that makes sense for you, and checks all those boxes of goals that you're trying to achieve. And successful implementation. So this has to do with, you can have the greatest design in the world, but as soon as that leaves the designer's hands, how many other hands is that going to go through? You have your construction team, you have the building operator, you have the people occupying the building. If they don't know what your intent was, you can have the best investment in the world on a great design, but it's not going to achieve it unless you make sure that you're going through a commissioning process, and you're also going through a measurement and verification process where you have those checks and balances to see if you're really getting the energy savings that you planned on. So hopping over to the next slide, this is our ZNE process. So we're starting very early, schematic design, ideally. We're going through these 5 phases. And we have, so preliminary design phase, that's with your schematic design. That's where you're getting your team together and really making sure everyone's on the same page. You're going to go through then into your advanced design, where you're going through your energy modeling and cost benefit analysis and really honing in that design. So preliminary design, you're going to be setting your goals. Advanced design, you're designing to those goals. Construction, you're constructing it, hopefully, to the design intent. And then the measurement and verification. So that occurs once the building is occupied and you go through your whole M&V process to ensure that you're actually performing as intended. And if you're not, that's fine. Most projects are not. And that's the point of all of this, is to have that M&V process so that you're going back and you're having those checks and balances to identify where controls and settings weren't put as intended. And you can fix it and then have your very efficient building. And so first step is project initiation. So that's going through, you're doing your application questionnaire, collecting data. Most importantly, you're getting your design team together. And that includes everything through commissioning. You need to have everybody there from the start so that you can set up even just your wiring, making, if it's new construction, making sure that you can set up your building in a way that you're isolating end uses and you can have that data so that when you see that your energy consumption is higher than it should be, where are you having those issues? Is it with plug loads? Is it with that weird pump that shouldn't be operating 24/7, but for some reason it is? That's where you get to like have that real tangible use data to help out. We have a kickoff meeting to make sure everybody's on the same page, and then have reoccurring monthly meetings so that we're on track throughout the whole process. And yes, it is a long process, but you reap the rewards at the end. So phase one, this is where you're setting your goals. And these deliverables, so you have 1.1, 1.2, 1.3, they are part of the project team's responsibility. But we stay there throughout the process and help facilitate this and provide additional analysis as needed. You have that charrette. The charrette is a really important part where you're getting everybody together to make sure you're not forgetting something. I've had recent conversations with a university that's looking to do a zero net energy building. And who needs to be at that charrette? Everybody. Like you're gonna have, we were talking about even having the farmers market folks from down the street join in because there's opportunities to be involved in something that you bring in the community in. You have the students involved, not just the university students, but we're looking at STEM programs that are around the area. There are a lot of things that you can be doing, and bringing everyone's voice into the room is really valuable. So that's phase one. Phase two is getting into the advanced design. So like I was saying before, designing to those goals that you set in phase one. The sub-metering, basis of the design, you're really just creating the best project that you can. And this is, our program is not technology specific. There's no point in this program where we're requiring you to, you have to have this type of control system. No, you don't have to have this type of HVAC system. You have to pick things that are all electric and meet your design intent. And as long as you're hitting that % reduction, you choose what works for you. I mean, every building is different. And then jumping into construction, this is the most important thing here is that construction kickoff meeting. And people rush into wanting to construct and they forget that we need to take a breath, look at what we have going on and who's involved. So that's really getting that commissioning agent and the construction team together so they can look at their schedules and say, okay, I need to look at the wiring before you close those walls, or I need to be like testing out the HVAC system before it starts running and before you connect it to whatever else you need to be doing. So this is a really important process to make sure that you're actually getting what you designed for. And this is where you're also working on your M&V plan to make sure that everything that you are installing at this point, you have up and running in a way that can successfully complete your M&V process after the fact once you have occupancy. And a little side note on occupancy, I get it. We don't have a lot of occupants these days in some buildings, more so in the multifamily. Occupancy schedules, everything's different now, and that's okay. And we are here to work with you in that process. So originally when we launched this program, it was, you have to be full occupancy or at least 80% and above. And we understand that that's not a reality these days. And we are here to work with you. So don't be afraid of that. So once a building is at least occupied as much as you're gonna have it occupied, and then we start the M&V process, make sure everything's up and running properly, testing all of your controls, just make sure that you're getting your bang for your buck. And then phase 5 is verification. So that's where you're really making sure that you have it all complete. You go through your M&V completion of your 12-month period. You have your real weather data, not just your TMY3 data, and you're looking at real occupancy conditions, and you're going back and you have your calibrated energy model. Typically, we recommend going with IPMVP option D, which is the calibrated energy model approach to verifying your savings. And in the end of the day, you have really good data that you can use as a case study, you can use to present to people. You can have dashboards in your lobbies where you can have tenants that are doing gamification approaches where you're trying to compete to see who has the least amount of energy consumption. There are a lot of different ways that you can use this data and the results and all the educational steps that you've gone through along the way to advertise for your building. Is great marketing. And you can use that to, oh, hey, in our building, you have no utility bills, like depends on how you set it up, but it can be a really valuable approach for lots of different avenues. The participants that we currently have, we have 11, and as you can see, there's a wide variety. And that's what I love about this program. There are, because it's a ZNE process and not like a cookie cutter approach, it's whole building, it's you do what you need to do and you get your percent reduction you need to do it in. And so we have office, warehouse, mixed use, food processing. They make really good salsas at this place. We have community center, educational facilities are really great. But we're also a museum. Look at that EUI. So the top EUI is their baseline, and then the bottom one is their goal. Even if you have some weird process load, that doesn't mean you can't save energy. You just have to look at the areas where you can make modifications to your building, whether it's an existing building, new construction. We can work with whatever you have. There's always energy to be saved. And so that's the main point to get across here. And we have recently modified our requirements for the program to now include multifamily. So in getting into the multifamily realm, we have decided to do a design guideline for multifamily, and that's what Sean and Umay are going to get into next. And this plays off of the fact that there is oftentimes, hesitancy to jump into an all-electric building and to know how to do it. Like, what are the steps if you've never done it before? And this guideline, it's a ZNE multifamily all-electric design guideline, and it goes through step by step what kind of energy conservation measures are necessary to get to that energy savings percentage, and what technologies are there. We can sit here all day and say like, okay, you need to have a twice as efficient system, but what does that mean? Like, what specific systems are out there that are going to meet these requirements? And Sean is now going to be taking it away and showing you exactly what that is, as well as case studies that I think you're doing case studies or referencing them. They will be in our guidebook that we will be releasing to the public early next year.
All right, thank you, Annie. So get this on full screen. All right, hey everybody. I'm gonna go through all electric multifamily design in Michigan. And to be honest, this cool project is in Erie, Pennsylvania. I'm using case studies from around the upper Midwest, but lovely project. Quick introduction. I've been involved in this demonstration house to the right, upper right there since 1995. Last night I was once again helping choose new co-directors. 2002 to 5, I was a high school science teacher. Then I worked as a construction and design project manager for a big local developer and started a new affordable housing division and learned basically there, that job was how I learned that all electric is less expensive to build and faster, to build one less piece of infrastructure. And then I spread the gospel on it's cheaper and faster since 2011 to today. As Redwood Energy's managing principal, we've got about a dozen staff and such, and we support projects like this. This is the first set of homes. It's 26 homes. These are all net positive. They're all electric. They get $200 bills back, checks back from the government, from the utility, pardon me. because they sell back solar electricity into the grid. And this cool project on the bottom, this is 11 stories and passive house and low-income housing in Washington, D.C. And it's got this cool 9-story tall solar array on the side of the parking garage because it honestly is just the most cost-effective way to build. Like you make money this way. So here's my old boss explaining the situation. All electric is a no-brainer. The cost of bringing gas to a building site is expensive. In our developments, all electric is less expensive to build and just as efficient or more efficient in operations. And you can't generate gas on site, but you can generate electricity with solar electric panels to lower bills. A lot of their financing is predicated upon solar power of an all electric building. That's like their competitive advantage. At the end, they usually can build an extra apartment and a half by solar powering it and adjusting the rents. So there's higher rents as utility bills go down, dollar for dollar. So they invest in solar and they reap the financial benefits, and it helps the project's finances enough overall that they make a point of it every single time. So I'm gonna go through water heating and then space heating. I'm gonna go from little stuff to big stuff. And at the end, I'm gonna show like, and we're also gonna talk about a whole bunch of other things in this booklet that comes out shortly. So here, left-hand side, this is a cool little all-electric passive house, row house in New York City. This is using a Stiebel Eltron tank here. This is the earliest ever heat pump water heaters in the US. Stiebel Eltron's leading brand in Germany, leading domestic hot water brand in Germany. This one here, Eco2 Systems, this goes all the way down to -30 Fahrenheit. These other tanks you'd put inside the envelope of the building. So you generally have them, you know, so they don't freeze basically, but the sand in it can go down to -30. These products, they would freeze up if they were at like 35 degrees Fahrenheit. The compressor would get covered in ice. So you keep those on the inside of the building. And in that way, you heat the building with a heat pump in the wintertime very efficiently. And then you use a water heater inside the envelope, reuse that heat. And that's also very efficient. So it's like a two-step process of heating the water. Is you first heat the house. It'll lower the temperature of a room by 1 degree over the course of a day. And they operate between an hour and 4 hours a day, depending upon how much water is being used. So maybe 30 minutes in the morning, 30 minutes in the evening, and they have as much sound as a dishwasher, 49 decibels. This is a kind of a neat advanced example of how to use these inexpensive tanks, which are built in the factory, in an apartment building. This is, instead of having like a 1-to-1, one for each apartment, they have 2 tanks that are serving 4 apartments, and the water goes into one tank and then it goes into the next. And this is to provide enough storage and enough capacity to support 4 apartments in a stack above. And there's a whole bunch of these little stacks down in the basement, just straight up. The straight up part, they're putting it through pipe and pipe recirculation. So the water leaves, it goes in this insulated pipe up, delivers water. And at the top, it just bends around. It doesn't go exploring the rest of the building. It goes turned straight back down inside the same insulated sheath so it doesn't lose heat. Because in a recirculation system, you can lose 1/3 to an equal amount of heat that you are delivering to the apartments. You can be losing it in the recirc system. So it can be a dramatic energy suck to have water going all over a building not very well insulated. So this straight up and down stack style is the most efficient and keeping the heat loss least. So in the left-hand corner, this is one of many cool apartment complexes that Pete Singer is doing up in upstate New York, like Rotterdam, Albany area. And he's experimented with most of the products that you see here. He's a big fan of the Arctic. In blue down here, you can see that these go to -4, -15, -22, -4, -4, -7. So beyond that temperature, you'd want to bring in electric resistance. To that temperature, they can do the whole job. So this is essentially at all moments of the year, with a polar vortex being an extremely, it's rare to get down to -15, right? So these are doing, there's refrigerant inside of them. They release refrigerant, it's hot, it goes to a storage tank, the refrigerant comes back cold, gets reheated. This sits outside of a building. And so these are air to water heat pumps, and they can handle like 9 apartments to 20 apartments, one of these like 3-ton products. So it's really, they're right size for a building of a campus. Here's another example. This is here in California. I apologize for not having a good example elsewhere of this particular type of tank. They exist, of course. I just couldn't find the right example at the moment. So using a Colmac is a large air source heat pump. It takes heat out of the air, sticks it into the recirc loop. And this is not a particularly efficient recirc system or anything like that. If you're doing this as a boiler replacement in Michigan, like a big gas flame underneath a big old tank that's recirculating heat through a building, in Michigan, you'd probably be starting with a Colmac CXV because it goes down to -4 Fahrenheit. And you could take it up to about 120 Fahrenheit, which is not quite hot enough. You want to be like 130, 140. So two choices, either an electric resistance element to do the last little bit, or feed this water at 120 Fahrenheit into a water-to-water heat pump, sort of concentrates the heat. So you can take it 120 to up to 190 at that point. You can do it into like the hot water you have for a radiator, which is at 180 Fahrenheit, 170 Fahrenheit, 160 even. So this range of products here can cover, depending upon which type of heat pump you're going with, they can go from -30 Fahrenheit up to 180 Fahrenheit if you use an air source and a water source. And if you just use an air source, you're going to be down at like -30 with the Sandin. You can use these in apartments, gang them up. One of these supports about 4 to 7 apartments. So we have installations where you just got a whole bunch of them. Those go to -30 up to 150 Fahrenheit. So anyway, you can combine these products. The whole point of the guide is to try to show you what your options would be. But any climate challenge you have, any temperature goals you have, those are accomplishable with standard products sold all over the world. This is a cool little example in Seattle. It's downstairs, a couple floors below, I think, in the parking garage, and they have all these air source heat pump Colmacs, a whole bunch of storage, big apartment complex. The company that designed this, Ecotope, they've done almost 60 all-electric apartment complexes with big central systems. My firm has done like 110 all-electric apartment complexes. We've mostly just used individual tanks, so difference in style. And I was always pursuing efficiency. They weren't trying to solar power theirs the way that we have goals and funding and obligations in California to solar power apartments. So I found individual tanks to be more efficient because they didn't have the recirc heat loss, and that was really important. The amount of recirc heat loss, you could think of it as, oh, well, like maybe enough to drive a car about 3,000 miles a year per apartment. So that's about the amount of like electric car energy way of thinking of it. Different, think about this, electric resistance versus a heat pump, that's about 10,000 to 12,000 miles of driving in an electric car per year. The difference per apartment from having electric resistance, which is very common in Michigan, to going to heat pumps, which is not very common. But that rationale of like, you can drive the entire year on that budget just for the hot water savings going from resistance to heat pump. Here's a nice example. This is in Philadelphia. The building is completely solar wrapped. You look through, when you're inside your apartment, there's solar panels framing your window and they're see-through. So light comes through. And this is Tim McDonald. This is a passive house apartment complex. He loves this. He's like, I'm gonna do it every single time now. Because he's got like 5 stories solar offset, got all the parking garage and the cars. And solar is so cheap that this is a cost-effective way for him to develop. You know, in California, there's a payback of 4 years. Other states might have a payback of 8 years, but if you're going to own a building for any significant amount of time, then it's cost effective. These products here to the right, these are HRVs, so they do this job of balanced ventilation, but when the air is going out that's been warmed by the inside environment and it's supposed to be pre-warming the air coming in, they're not casual about that. They stick a heat pump on it and it sucks all the heat out of the exhaust air and sticks it into the incoming air. And so they don't have a low temperature. They can go as low as you can go. And they're not providing a ton of heat. So it's appropriate for a passive house. These are producing like 9,000 to 11,000 BTUs at 47 or 5,600 BTUs at 17 Fahrenheit. They top out, like they bottom out, pardon me, around 4,000 BTUs an hour. So it has to be passive house. But if it is passive house, this is your whole house ventilation and your heating system. They're about $6 grand a piece. So They're a hybrid combined kind of thing. Package terminal heat pumps. So this has taken California by storm. Affordable housing developers are really into these ANOVAs. And they go down to -14 Fahrenheit. And it's a package terminal heat pump that sits on the wall. Unlike these ones over here that go through the wall or sit in a window, these ones, they are on the wall. There's a duct that comes in, a 6-inch duct, and a 6-inch duct that goes out, and it just pulls air through the wall, the machine, and then back out. And so there's very low profile. Like you don't really see much disturbance to the facade. There's just a couple little innocuous events there. So Innova and Olympia are both the products that fit that form factor, how it looks and works. And these ones are examples of, these are heat pumps. They can do heating and cooling, but they're really small. They got electric resistance at 40 degrees Fahrenheit. These ones have inverters. They're silent. They can heat the whole house. So this is the reason why people are excited about them, is they're the least expensive possible way of doing it. They're in the like 30% less expensive than ductless mini splits. Now, a ducted standard system, like these apartments here in Michigan, oh darn, I don't have my notes, but downtown Ludington, that's what this one's called. They're using like a standard square heat pump compressor outside. You can see these are examples of ones that go -10, -5. An apartment doesn't need much more than 2 tons, 24,000 BTUs. That's all apartments would ever need. And so it's small. And these are the kind of products that are being put into Ohio. Energy Smart Ohio is a contracting firm that electrifies people's homes. And he's putting in 2 to 3 tons, which is very modest, into people's homes. And then you just run them like they want to. They want to be sort of run continuously, as opposed to turn on and off like furnaces do. So you get a house that's just completely warm and quiet, as opposed to a house that's hot, cold, and kind of noisy because the ducts are blowing a ton of air to try to get the place warmed up because it's been off for 15 minutes or whatever. So this is nice, even warmth, very quiet. So the idea of a mini split is that there's a small compressor and it's split by a line of refrigerant to the fan coil inside. So these are ducted ones, sort of a hybrid, a bit of this one here, big old cube. More popular in Eurasia to go narrow and tall to save space. So this is what the ductwork looks like up there. Ducted mini splits, these are all super cold, appropriate. These are ductless, so have a fan coil on the wall, like that thing there. I think this was, this New Bedford, is that what it was? Forgetting the name of that one, apologies, it's at the top of my head. But anyway, I'm presenting, I don't have my notes there, darn it. So Hayer does -31 Fahrenheit. That's the coldest of our air source heat pumps. And there's efficiencies in just going straight to a fan coil, not blowing air through ductwork. So you're gonna find the coldest temperatures possible with ductless mini splits, if that's your goal. Over here on the right-hand side, these are double deckers. And they, as you can imagine, just do a lot more work. Maybe you shouldn't even call them mini, but that's how people that's the words people use. So Mr. Cool is a great example. One of these was installed, I saw a 10-minute video. It was -24 degrees Fahrenheit outside, and it was 70 degrees Fahrenheit inside, and it was a 1940s not well insulated house, like R13 in the walls. Had no problem keeping up in Grand Forks, North Dakota, the coldest city in continental United States, in January in the middle of the night, 70 degrees Fahrenheit inside. So this is with no electric resistance, just working as a heat pump. VRFs, this is just a bigger version of a ductless mini split. What's going on is they run refrigerant into a big box inside, and then the manifold box distributes that. This is the most expensive way to do a heat pump, just so you know. That extra refrigerant box and the controls and the alarms, that's the most expensive part of it. So maybe you do this if you don't have much space because you have one big compressor outside, but you don't do it to save money. As an example, this is $23,000 an apartment in Maryland, whereas ductless mini splits were $13,000 an apartment. The savings were so significant that they built a balcony on every apartment for about $6,000 to put the compressor. Everyone got a balcony then, and they still saved like another $5,000 to $6,000 an apartment compared to VRF. So you don't do these unless you kind of have to, because they're wicked expensive. This is the cheap version. Sort of, this sits in the wall. So a VTAC on the side of the wall, you'll see a grill outside. The ice air, that's the one that does the coldest temperatures. And Friedrich as well, that's a very nice quality product, Friedrich is. So this is for ducting, sort of cheap ductwork in an apartment. You put a little closet in, you blow the air down the hallway, split it off to the rooms. And this is not cheap. This is ground source heat pumps. This is another Philadelphia project here on the left-hand side of that nice canopy of solar. It's a zero net energy project, passive house. And they did wells straight down into the ground to put in these ground source heat pumps. Once again, expensive. This strategy was replaced by that super cheap one I showed you of 2 tanks and a vertical pipe. This is an earlier effort by the developer, learned lessons how to make even more money, spend less money. This is a fun group. This is an architect that's a brother, a contractor's a brother, and the sales dude is the brother. And they're really tight. They understand how to build and make profit. So I want to say it again, that solar array is a profitable solar array. It's done on purpose to make money. Last slide. I want you to see that the booklet contains not just sort of this guidance around HVAC and domestic hot water systems that I'm trying to present on, but also this is a $1,000 induction range. This is the combined washer dryer. It's very affordable and it just does everything in one box by LG. This is like a backpack electric leaf blower. This is your battery powered snow blower. Down here on the right, this is when I started a fire with no lighter fluid. My brother used to do that and pour it on the grill. And one time he did so much, I literally just vomited. Like all of the lighter fluid in my stomach, just hurled it out. So this is a way cleaner way to light your barbecue. The new electric Hummer, you know, sort of a Michigan-made kind of deal here. This is a car charger, but it's also a solar inverter, and it can take the power from your car and power your house during emergencies. Akkoseoglu, coming out of Canada, this is called the DC Bell. Wallbox is making another version called the Quasar. But to take energy from your car and power your house during emergencies is the way that was sort of developed after the big tsunami in Japan in 2011. Nissan started doing that, and it's caught on all over Eurasia, and now it's come to the United States. And last but not least, on the left-hand side, that beautiful fire, that's mist that's been made by an ultrasound with LEDs underneath it and a heating element in front. So it's a completely safe, beautiful fireplace that looks like fire, but isn't, and is safe. And then you can just get rid of the whole expensive gas connection to the building, which is anywhere between like $1,500 in rural areas up to $100,000 in Los Angeles. In cities, it gets just crazy expensive when you start working in the streets. So with that, I will stop sharing and hand it off to Umay.
Thank you, Sean. Okay, let me, cool. Okay. Good, I hope. Cool.
It's good.
Hi everyone, I'm Umay Akkoseoglu from DNV-GL. I'm an energy engineer and I worked on the energy modeling of the multifamily building for our design guidelines. I'm going to go over the steps of the energy modeling effort that we worked on to provide a detailed pathway to achieve a ZNE ready new construction multifamily building in the Michigan climate. The purpose of our energy modeling effort is to provide a supporting guideline to assist the building owner and the design team to achieve a high performance design and all electric solutions for their projects. The first thing I want to talk about are the choices we made with the energy modeling. According to the Grand Rapids City housing data, after single family housing, the second largest sector is multifamily buildings with 50 dwelling units and more. And the one that follows it is the multifamily buildings with 5 to 9 units. Because of this reason, we decided to do 2 energy models, one for a low-rise multifamily building and one for mid-rise multifamily building. For the software, we chose the RAM-Rate software. The reasoning is because on top of calculating the general energy modeling needs of energy consumption and cost of operations, RAM-Rate software is capable of conducting home energy rating system ratings for the dwelling units. And the software also includes an hourly simulation engine on top of the traditional seasonal engine. It is also capable of, in addition to these, it is also capable of performing various different analyses, such as Energy Star multifamily new construction home analyses, DOE certification, and reporting the compliance with Energy Code of International Environmental Conservation Code for 1998 code to 2018 code. For our energy model, we went through multiple energy conservation measures, which are also called ECMs. We first started with a passive building design, which means a system or a structure that uses natural energy source such as sun, wind, or temperature difference to achieve results without being connected to electricity. And then we follow the right steps, right order approach through an iterative modeling analysis. The first two ECMs that we applied, it focused on improving the thermal performance of the passive building components, which is to reduce the cooling and heating loads of the building, which include roof and wall insulation and glazing. Once these passive strategies were implemented onto the model, we worked on ECMs that for the additional savings and comfort that can be achieved with increasing the performance efficiency and reducing the runtime of the active systems, such as the appliances, plug load, domestic hot water, and the HVAC systems of the building. To break down the energy conservation measures that we implemented, the first one we implemented is for the building thermal performance, the ECM1. We improved the thermal insulation of the building by increasing the wall insulation to be rock wool insulation for the cavity with additional 2-inch exterior rigid insulation. This insulation increase brought the assembly R value of the walls to be 21. We also added an exterior board insulation to the roof, which resulted in an assembly R value of 50. For ECM2, we upgraded to a high-performing triple pane glazing with total assembly U value of 0.2 and a solar heat gain coefficient of 0.23. We followed this with ECM3 and replaced the baseline appliances with high-efficiency Energy Star rated appliances. We replaced the baseline electric dryer with a heat pump ventless dryer. And for the stove and oven, we replaced with an induction range and a convection oven. ECM4, we switched 100% LED fixtures and implemented smart plugs to manage the receptacle load of the building. And ECM5, we provided mechanical ventilation through energy recovery ventilators or ERVs. After ECM5, we actually decided to go 2 pathways. One being a high efficiency pathway and one being the premium efficiency HVAC and domestic hot water systems. For ECM6A, we decided with the high efficiency hot water replacement of the tank resistance electric water heater that was in the unit for the baseline. We replaced this with a heat pump water heater with a UEF value of 3.45. We followed this measure with ECM7A, the high efficiency mini split system to replace baseline package terminal heat pump system for the unit. This new system has SEER value of 24.4 and HSPF of 12.8. For the premium efficiency pathway, we went with a heat pump water heater of UEF 4.0 and followed this with a premium efficiency mini split system of SEER 29.4 and HSPF of 14.0. Then we looked at the impact of these ECMs. The way we did it is by looking at the reduction in the annual energy use intensity of the building and the annual cumulative energy savings that we get from the addition of each measure. As Annie mentioned, the annual energy use intensity is the kBTU consumption per square foot of the building. So for the baseline, we started with a 40.1 kBTU square foot, which the baseline is the IECC 2015 code equivalent low-rise multifamily building. And if you guys can look at the last two, which is the 7A and 7B, the 2 pathways cumulative EUIs both got down to below 25 kBTU square foot. And on top of that, we were able to achieve above 40% savings for both pathways. These are great values because looking at the 40.1 kBtu square foot, we actually based this off of the 43.9 value that we got from the 2030 AI directory for the national average EUI for low-rise apartments. And the 40.5% savings that we got from the high efficiency pathway and the 41.5% savings we got from the premium efficiency pathway both meet the requirement for our Consumers Energy ZNE Companion program, which requires 40% savings for all new construction projects. In this slide, I just wanted to break down the EUI a bit more based on the end uses of the building. The main takeaway here is just seeing the two largest end uses of the building that has the highest consumption is the space heating and water heating, which is why exactly we wanted to go two pathways with the high efficiency and the premium efficiency in terms of reducing end use energy, which result in a lower overall building energy, as you can see from the chart. As we go from ECM 5 to ECM 6A or to 6B, we can see that the biggest drop is from the domestic hot water, and we can see the same thing for the switch to the mini split systems with the ECM 7A and 7B as well. This slide is more of a recommendation slide because although the ZNE program cannot incentivize renewables at this time, we wanted to see what the benefit will be in the model if we generated electricity on site. So what we did is we modeled a 29 kilowatt solar top roof array that generated approximately the building's annual energy consumptions by 70%. From this chart, you can see that if the energy benefit of the solar is considered, the resulting net energy consumption of the proposed case is an EUI of 6.8 in net energy consumption. The other thing we wanted to show on this chart is the comparison between an all-electric baseline and the code equivalent for mixed fuel version. From the left example, the standard mixed fuel, you can see that the annual energy use intensity of the mixed fuel is much higher compared to the all-electric baseline, with a 62.2 kBtu per square foot compared to the standard all-electric baseline of 40.1. Lastly, we worked on the measure costs of the measures we implemented onto our energy model. We used regional cost data and investigated both cumulative and isolated costs for the measures material as well as labor equipment costs. I have to say that the results we have so far are preliminary at this time, but they will be finalized by the time that we publish our design guidelines in early 2021. But for now, what I can show is a breakdown by ECM payback periods. To start off, the ECM 1 and 2, which are both for the improved thermal insulation and high performance glazing. The payback period for these measures are pretty high, solely because the IECC baseline for thermal envelope in Michigan climate is already very high performing. So we have negligible first cost, but also accompanying with negligible savings because the baseline is already very high for these measures. And however, there's great additional benefits to improving your thermal envelope, such as occupant thermal comfort and the building's resiliency. Then following the ECM 1 and 2, high efficiency appliances we implemented with the ECM 3, the Energy Star rated appliances, their isolated simple payback is only 4 to 5 years in total to pay back with the savings you get from these measures. ECM 4, the LED lighting and plug load, you can pay it back in the simple payback for these is less than 1 year. Heat recovery ventilation, the ARV implementation, these are also only 4 to 5 years of payback. Following this, we just wanted to show the premium efficiency since these are a bit higher priced but higher efficiency models for the domestic hot water and space heating. ECM 6B, the premium efficiency domestic hot water heat pump water heater. You can the simple payback calculated for these measures in an isolated way is just less than 7 years. Similarly, the the mini split systems that you would have in the unit replacing the packaged terminal heat pumps is also less than 8 years with their savings, the savings that they contribute to the energy model. Again, this is all preliminary because we have to get it vetted with the market before we can publish it with the guidelines, but we wanted to provide these values as they prove the more reasons to go all electric ZNE pathway with your new construction multifamily. So I hope I have you all excited for more of to come with the new construction multifamily design guidelines. And the design guidelines we're going to publish will include this type of energy and financial analysis for both low-rise multifamily and mid-rise multifamily apartments. We put a lot of work into this with the intent that it can be comprehensive and informative document to achieve all electric performance on your multifamily projects. And now I'm going to give it back to Annie to provide a bit more detail on participating in the Consumers Energy ZNE program. Thank you.
Okay, thank you. That was great going through all of those different steps, both of you, Sean and Umay. This is a lot of really, I mean, technical information, but great stuff. I hope everyone got a lot out of it because, you know, we've been working hard on trying to help make the ZNE process tangible for everybody here. And so my final comments are, you know, we're open for enrollment. If you're interested in being part of this program, please contact me. I think Jillian is going to also be adding some links as where you can get some more information about the program. And as soon as we have this this guideline ready to be launched, which will be earlier, probably January or February of next year, once we go through our full review process. So that'll be available, and we'll make that known to everybody that we can. And thank you for being here and listening. And we are ready to do some Q&A. I'll give it back to Jillian to go through these final slides, but thank you all.
Yes, thank you. And thanks for the robust conversation going on in the chat. I'm learning so much from Dana and Sean and Brett's perspective. So folks, if you're following that chat, if you have questions about it, you know, type them in either in the chat or the Q&A. We'll be able to keep track. And if there's anything that we can connect you with, let us know. So of course, I have my own questions, but to address the ones that are in the Q&A right now. So they've been written answered. Thank you so much, Sean. For folks who are not able to see these questions, I'm going to repeat them, and maybe Sean, you could answer them as well. Drew asks, Sean, are these systems scalable to single family residents? And if so, would it be affordable in Michigan where the sunshine is not constant or consistent?
Yeah.
Sorry, Drew.
So, I personally have 4 zero net energy all electric tiny houses, so it goes all the way small. And then we're working on everything, you know, like that 11-story tall, massive affordable housing on the Washington, D.C. Beltway. The solar availability around the country varies between, I'm in the worst case scenario of about 1,100 kilowatt hours per 2 sheets of plywood worth of solar panels, a kilowatt, which is about that much, a little bit less than 2 sheets of plywood, but about 60 square feet. So I'm in the worst case scenario, Seattle's in the worst case scenario. Solar makes a huge amount of sense here because electricity is expensive in California. It doesn't make as much sense in Seattle, where they have lots of hydropower, which is much less expensive than California's grid mix. And also the nature of utilities. If you have a gas and electric utility, they drive electricity rates up, they drive gas rates down, just like countrywide. They do that because gas infrastructure is more profitable to put in, so they make sure costs are low there. Electricity is not profitable to install, which is 80% of the business of utilities, installing infrastructure. So you always have to think, why are they doing that? Oh, it's because they make more money installing the infrastructure. Not that surprising of an answer, really. So the Michigan is in the 1,300 to 1,500 kilowatt hours per kilowatt. You're a little bit more, but your electricity is less expensive. So I don't know, Maya, have you done an analysis of the cost of solar versus the benefit in California? Sorry, in Michigan?
Yes. So I am working on that right now. We did a preliminary cost analysis, and the cost payback seems like a 4-year term if in the size that we are talking about, but obviously the size we put is to cover the 70% of the energy of the building, consumption of the building. So depending on the size of the solar array that you can provide to the building, that year will change. And
what I've seen is that PV has accelerated depreciation and a tax credit. And if you are personally installing a lot of it, it's literally free. So it's $1,500 a kilowatt to install just with your materials and the least amount of labor. When I work with big companies that do a lot of this, they get free solar installed just with those two things, the investment tax credit and accelerated depreciation. When we had rebates on top of that, developers made money in California installing solar just on a cash in out basis at day one. Paybacks we see, the other thing to think about is that solar can be as little as $1,500 a kilowatt to install, and it can be as much as about $3,500 with a not so affordable contractor or kind of a trickier installation. If you saw north of $3,500, you should have gotten a second bid because it's $1,500. So the cost effectiveness of your price of electricity versus the price of solar versus your solar productivity is those three things that are going on. But basically, solar is profitable in every state that allows it. If you can do virtual metering, the question is it no years, 4 years, 8 years, 12 years is kind of the range of worst case scenario to best case.
And I'm going to chime in with a little like factoid here. You know, you were mentioning the like 1,200 to 1,300 kilowatt hours per kilowatt installed that for Michigan area. And for like a reference, like in San Diego, I know it's like 1,600. So it's not cutting it in half. You know, cloudy days you still are generating energy on cloudy days. And so I know it's easy to think like, oh, it's cold, oh, it's cloudy, you're not going to get the same kind of generation, but it's not completely on off because the clouds are there.
So
Yeah.
would you say that a misnomer is that, oh, when the wind doesn't blow and the sun doesn't shine? Because I remember a professor saying to me once, if you can see, then the solar panel can do some work too.
Yeah, exactly.
Okay.
Yeah, the solar panels start making electricity the second the sun hits them, or through clouds. And there's also the fact that cold days make solar panels much more efficient. They don't like how hot it gets on sunny days sometimes. So a crisp day in the fall or the spring can be just as good as a summer day because of the chilliness of it and clear skies.
You know, folks, you're mentioning all these fantastic examples, and I see that there's some checking in the comments to make sure that is this in a climate zone that is relatable to Michigan, and sometimes, well, always, almost always, California is leading the way in technology, but something that can be rebuttal to that is, oh, California isn't like everywhere else in the U.S. So they can do these things. Could you kind of address that? What is myth? What is fact? Concept?
Thank you for asking that. Okay, because since 1950, the majority of water heating in the United States has been electric. Since 1970, the majority has been electric for HVAC. 65% of all stoves that are sold in our country are electric. 88% of all dryers are sold electric. California is the worst case scenario. We're a petro state, and we've had an energy commission that was freaked out by the energy crisis of 2000, which was an Enron like gas management scam that they went to jail for and one committed suicide. You know, it's like that was an actual scam. And we built a whole code in response to that, like, oh no, if we rely on electricity, then things will go out. We've never had a problem since. We regulate our electricity again, and we don't have scams. So, or they're small scams. So that we are a worst case scenario. Almost 99% of buildings in California have had gas installed since about 2012. And my effort has been to like remind everyone else in the country finds it less expensive like to build. And if we use heat pumps, then we don't rely upon dirty electricity from the grid. And so once we established that it was a decarbonizing and it was less expensive, the Energy Commission since about 2016 has been, okay, we hear you, and they've completely switched, and now all of our state requirements are saying to build all electric for decarbonizing reasons. But everyone else since like the 50s has figured it out. One less piece of infrastructure has multiple benefits of getting rid of it. And if your electricity is affordable and decarbonized, you get to decide how efficient you want to go. And if you want to take advantage of solar, honestly, that difference between electric resistance tank and a heat pump, that's 2 kilowatts of PV on the roof to 3. So we're talking about like 3, well, that'd be 1, 2, 3, 6 sheets of plywood, more solar on the roof that you have to install because you put an electric resistance tank versus a heat pump tank, which has made it very easy just to switch everyone to heat pumps. Because it's a waste of money to put all that solar up just because you put it in a resistance tank. Just put the heat pump tank in the exact same spot, walk away, put a vent on the door so it doesn't suffocate in there. But
and Umay and Annie, do you have anything to add to that? Thank you, Sean. That was incredible.
Oh, just a minor thing to add on Sean's credibility here. Although he is from he's living in California. I don't know if everyone caught it earlier on. He is from Wisconsin, grew up on a farm in Wisconsin, so he does know the climate. So don't hold the whole California thing against him. He does understand.
you betcha.
Oh yeah, you betcha. Eh?
You betcha. And so,
Oh yeah. Oh my God, that's so funny. So I'm so tempted to keep this conversation going. It's so full of good content. There's questions that have been answered in the chat, and questions I've written down, questions that have been sent to me as the moderator. I'm gonna have to invite you again when the guide is done, because I feel this conversation can be going much more than an hour. So since it is 12:01, we will have to be wrapping it up. So folks, if you are interested, I know there's been a lot of conversation. You know where to find me, Jillian at usgbcwm.org. Get a hold of these emails that you see right here, contact them, call them even, that's bold. And thank you so much for being here, folks. So can you go to the next slide, please?
Yep.
Okay, take your time. Okay. So again, thank you so much to the speakers, Annie, Umay, and Sean. You are incredible guests. We're so fortunate to have you on our Afterglow series today.
It was a pleasure.
Yes.
Yeah.
And so folks, for more information coming up on this, everybody on the call and more, we're going to be starting this same Afterglow series back up after the holidays, January 7th, same time as always on Thursdays. We haven't changed it. Retro commissioning, a deep dive. Okay. So our visionary sponsors, thank you so much. We cannot be doing our good work without you. Consumers Energy, DTE, EEL, WEGI, and everybody else who sponsors the chapter as members. We see you and we appreciate you. Don't forget to check out the survey that's coming out. Those are probably the most important thing to us. And can't wait to see you again. So thank you, everybody.
Bye. Thank you.
Take care.
See ya.